We have so far studied what's called simple harmonic oscillation, in which the only net force exerted on the object is a linear restoring force, such as the force from a spring. We know that force is conservative, which means the total mechanical energy of the system is conserved, and we studied that before. In reality, though, when you consider any simple harmonic system, such as, a pendulum, the pendulum is not going to swing forever, right? If you pull it to the side and let go of it, it's going to swing for a number of cycles, and the amplitude will get smaller and smaller. Eventually, it's going to stop. The same thing happens to a block attached to a spring, and after several cycles of oscillation, it will slow down, eventually stop. So what is going on here? Because, well, in the real world, there is always some resistance force, friction, that is, that will take energy away, take mechanical energy away from the oscillation system, and that energy, of course, is turned into heat and sound and other things. So we must, if we want to consider a real-life situation, add a resistance force. And the resultant oscillation is no longer simple harmonic oscillation, rather it's called damped harmonic oscillation, or simply damped oscillation. There are many different forms of resistance force. For example, if you consider a solid object going through a fluid, okay, such as air and water, one way to express the resistance force is something like a constant times speed squared. The speed squared is a quadratic form, and that will add a lot of complications to our differential equation. In fact, it's going to make our differential equation non-linear, so we're not going to deal with that. We're going to deal with the simplest type of resistance force as far as the solving equation is concerned. And that type of force is called linear resistance force. In other words, you do get a resistance force, okay, Fr, R standing for resistance. Okay, it is negative, meaning it's opposite to the direction of motion, and it is linearly proportional to the velocity, negative v, with, of course, a constant in front of it, b, which we call b. Okay, again, this is not the only type of resistance force, but as you will see in solving the equation, since F is directly proportional to v to the first power, is a linear resistance force. That makes our calculation a lot simpler. So, with that new force added in, let's look at what happens in x direction. Okay, what is the net force in x direction? Well, of course, I have negative kx. That could be a real spring or an effective spring. Anyhow, that is the linear restoring force responsible for the oscillation. But on top of that, you also need to add this term, the resistance force, minus bv. Okay, v really is just dx dt, as you know, right? So that's the net force. What does that equal to? That equals mass times acceleration. So mass times acceleration, which is the second derivative. Okay. And my question is, with this new force added, how does that change the oscillation? Okay, we can look at this problem from math point of view and from physics point of view. From physics point of view, you know when you add this force, okay, this force always resists motion, right? Because you see, it is always against the velocity. So when the object moves forward, this force is backward. When the object moves backward, this force forward. It always tends to slow down the motion, and therefore, with this additional force, you're not going to move as fast as before. You're going to lose kinetic energy, and that kinetic energy lost is not turned into potential energy, such as in the case of this term, and rather it's turned into heat and sound and so forth. Therefore, you're going to lose mechanical energy overall, and we know the mechanical energy of a simple harmonic oscillator at a certain moment when its amplitude is A is always 1/2 Ka squared, right? And as the mechanical energy is lowered over time by this resistance force, we know the amplitude has to decrease as well. Okay, so if I compare our new oscillation with this damping force with the previous simple harmonic oscillation by doing a plot, okay, here is t and here is x. Okay, without the damping force, you know the amplitude is fixed because the energy is also fixed, is always fixed. It's like this, okay? The amplitude does not change over time. So what happens with this new term added? Well, we know the energy is going to decrease over time, and therefore you're going to have a situation like this, right? You have reduced amplitude over time. Okay, in other words, the amplitude tapers down like this. So that is the first thing that we have to consider. Okay, the amplitude is no longer constant, but rather it decreases over time. That's one thing. Another thing is, what happened to the period of the oscillation? Okay, in other words, does this term slow down or speed up the oscillation? Well, of course, the answer is obvious. This term always resists motion, therefore it tends to slow down the motion. Therefore, you can imagine when you add this resistance force, the oscillator is going to take more time than before to complete one cycle, because it's always opposed by this additional force, and therefore the period tends to get longer, or the frequency tends to get lower. Okay, so again, these are the two new things from physical consideration when you add this new term, and that is, first of all, the amplitude would decay, and secondly, the period would get longer, or the frequency will be lower. That's from physics consideration. Okay, mathematically, let's look at this equation in detail. You have here x to the first power, here is dx dt to the first power, here is the second derivative of x with respect to time. There is no such thing as x squared, for example, or sine x, cosine x, whatever. So every term is proportional to the x to the first power, so that's good news, because that means this is a linear differential equation, which is rather simple to solve mathematically. Okay, the idea is this. You have x, you have dx dt, and you have the second derivative, right? And they have, when you move this term to the other side, you find these three terms will add up to 0. Now, what does that tell us? It tells us that you are looking for a solution x as a function of time, okay? X as a function of time, such that this function itself and its first derivative and its second derivative should assume the same functional form. It should have the same dependency on time. That is why this term, this term, this term, you add them together, they can cancel out, right? See, if this depends on e to the power t, and the next term depends on sine t, you know, they're never going to be able to cancel each other out for all time, right? So therefore, you are looking for the same functional dependency. Okay, so now the question is, what kind of function behaves in such a way that when I take a derivative and when I take a second derivative, it goes back to itself? Well, the only thing we can think of, actually only two things we can think of. One is an exponential function. The other would be a sine cosine function, right? Now we know without this term, it's a sine cosine function. Okay, so what happens with this term? Okay, without this term, it will look like this, right? The solution, simple harmonic solution, we're very familiar with it now. It's a, right? And then cosine omega t plus initial phase angle, phi initial, right? We know that by now. With this new term, how should I adjust this? Okay, how should I adjust it? Well, first of all, the amplitude is no longer a constant. Rather, it decreases over time. Now, do you expect it to decrease linearly over time? Well, if it decreases linearly over time, then it's going to stop, right? If there is a sharp cutoff at some point, it just completely stops. Does that really happen like that? Well, see, in reality, as the amplitude decreases, so does the speed, right? The average speed. But you see, this term, the resistance force, is proportional to the speed. What does that tell you? It tells you initially when you go very fast, okay, with large amplitude, this term, the resistance force is large, which means it's going to take a lot of energy away per cycle, okay? But gradually, as you slow down, and slow down, the amplitude is so small and the speed is so small so that this resistance force automatically decreases because it's proportional to speed. Therefore, energy is still taken away from the system, but at much slower rate, which means the amplitude is not going to decay linearly. Rather, it's going to decay, but it's going to keep on going for a long time. In other words, I can expect the amplitude to decay like that, okay? And the amplitude itself will decay like that. So this is a as a function of time, and this t itself. Something like that, not a straight line. That's more reasonable, right? Now, tell me, what do you think this looks like, this curve? How about an exponential curve? Huh? Because mathematically there's a good reason, because the exponential curve, the exponential function is such that when you take derivatives, it goes back to itself, right? And that's what we want, right? We want derivative and second derivative to have the same functional form as x itself. So how about if I do this? I say e to the power negative some sort of constant c times t. Now, why a negative sign? Because we know it decays instead of going up exponentially over time. So this is our what's called trial solution. Okay, this is our trial solution. We have a constant c to be determined, and we have this new omega to be determined. By the way, this omega is not the same omega as we had before. It is not the square root of k over m. Rather, we expect to be a little bit lower because, again, we have a resistance force that slows down the motion. Okay, so there we go. At the next step, all we need to do is take this, plug this into the equation, x substitute by that, and you take dx dt, okay? You take second derivative. Now, it's not hard to do, but it's a little tedious because, after all, it's a product of the exponential and cosine function. You take derivative, one derivative, you get two terms, right? And you take two derivative, you got more terms coming out, but it's doable. Okay, I'm going to leave out the derivation mathematically. It's just a little tedious, that's all. But when you plug it in and you compare the two sides and make them equal, you'll find that this indeed solves the equation. Okay, this trial solution indeed solves the equation with two conditions. Condition number one, what is c equal to? Okay, c must equal to b over 2m. That's one thing. So that's the decay constant c. Another thing is what's omega equal to? Okay, omega must equal to the square root of k over m minus something. What is that something? b over 2m squared. Okay, if c equals this, omega equals that, that turns out that this solution indeed solves the equation. I mean, you don't have to take my word for it. You can plug c like this and omega like this in, and you just take one derivative, two derivatives, see if the two sides match. They definitely will. Okay. So here is our solution. Here's our solution. A e to the power b over 2mt, and cosine omega t plus phi initial, and here's omega. Now, let's look at the physics of c and omega. Now, first of all, look at omega. Omega indeed is less than the square root of k over m. That will be the frequency, angular frequency of free oscillation without any damping, right? We know that with damping, you can have a lower value than that because damping force slows it down. Okay, that's one thing. But I don't really mind if the damping slows down the motion a little bit. But what I'm really worried about is that we're looking at a square root here, right? And there is a negative sign. Okay, so there is a danger immediately, and that is, it is possible mathematically for the second term to exceed the first term. And what will be wrong with that? Well, then you wouldn't have a real value for omega anymore, right? You have it, you have a negative value under the square root. That is a complex number, and that's not what we're looking for. So what does that tell us? It tells us that if you want to sustain oscillation, okay, you want to sustain oscillation despite the presence of friction, of resistance like this. Okay, you want to sustain an oscillation, right? You want to make sure that omega remains a real number, which means k over n must be greater than the next term, okay, which is b over 2m squared. And if that is not satisfied, then omega is an imaginary number. You're not going to really have an oscillation at all. Okay, so we have three possibilities when this first term is greater than the second term, equal to the second term, or even less than the second term. And then we're going to have three different physical situations. So situation number one, okay, that's when k over m is greater than b over 2m squared. So you see, you have a damping constant b, but it's not very large. It is small enough such that k over m is greater than that. Okay, now what that tells us is that omega is real. There is real damping, okay? There is real damping. So in this case, the damping, there is real oscillation. And in this case, the damping is there, but it's not very strong. We say it's under damping. Okay, that's the term we use to describe it, under damping. You have an oscillation, even though the amplitude does decrease with time. Okay, that's the first situation. Now the second situation, is when k over m equals the second term. Okay, so let's write that down as well. You have k over m. That's case b, okay? K over m equals b over 2m squared. So the damping constant b is large enough so that these two terms are equal. So what do you get as a result? As a result, omega equals 0, right? So when omega equals 0, you don't have the exponential, you don't have the cosine term anymore. Look, let's bring back. Omega is equal to 0. Okay, this cosine function has no time dependency, so it's just a constant. I can just throw it away. It's just some sort of constant that you can bring into that constant a. So all you really have is just an exponential decay function. So you have, the oscillation does not exist anymore. This is x, this is t. It's gonna look like this. Okay, no ups and downs. This type of damping is large enough so that it kills all the oscillation. But if b is slightly smaller than that, you are going to have oscillation. Okay, so this b is barely large enough to kill all the oscillation. We call it critical damping. Okay, critical damping. Okay, now third case. What if k over m is less than b over 2m squared? Okay, so in this case, omega is not real. All right, omega is not even real. There is no oscillation. Okay, there's no oscillation, and so what you have here is just x and t. It just goes down like this, monotonically. It does not oscillate at all. And what do we call that? We call it overdamping versus underdamping, of course. Overdamping. There is too much damping going on that no oscillation can sustain. Okay, so you have three possible cases: underdamping, critical damping, and overdamping. If you want an oscillation, of course, you want B to be small enough so that we can have underdamping. But critical and even overdamping, these are not totally useless. Can you give me an example of critical or even overdamping? Well, here's a possibility. Imagine you open up a door. Okay, a lot of these doors, such as the door to our classroom, they're spring-loaded, right? They're spring-loaded. So the reason why they're spring-loaded is because when you open the door, when you go in, the door is going to close by itself. You don't have to close the door behind you. It's going to close by itself. But do you want this door, after you enter the room, do you want to swing back and forth, back and forth, back and forth many times? You don't, right? You just want it to swing nicely and close itself. Okay? So you think of this door as an oscillator. Do you want the oscillation to be underdamping, critical damping, or overdamping? Well, you probably want critical or overdamping, right? So what you do is you add enough resistance into the spring so that when the spring pulls the door back, there is no oscillation. It just closes by itself. Okay. Another example would be the needle of a fine balance. Okay. So you have a balance like this, right? And this is where the needle will settle. But the thing is, if the balance is very fine, then chances are it's going to swing to this side, swing to that side, swing to this side, and that side, and so on. It's annoying. Okay, it's going to take a long time before it stops. So if you add some damping mechanism, in particular, you can use a magnet to introduce a magnetic damping force. Okay, that can hopefully bring this needle into critical or even overdamping, so that if it can go nicely and settle immediately after a little bit of time. It's not going to go into oscillation on and on forever. Okay, so these are the three possibilities. Next, let's look at the value of C. Okay, so the amplitude as a function of time is A, that is just a constant, e to the power negative ct. C is b over 2m. Okay, so b over 2m t. The damping constant, the decay constant here is b over 2m. First of all, you can verify easily that b over 2m has the right dimension. Okay, what is the dimension of b? Well, you know the force is given by negative bv. Okay, so b has the unit of well, actually, let's look at it this way. You know kx, that's the restoring force. Then you have bv, right? B dx dt. That's the damping force. These two obviously have the same. These two obviously have the same dimension, right? Because they're both forces, and that tells you what the dimension of B is. Okay. What is the dimension of B? That's the dimension of kx. Actually, x and that x cancels. So the dimension of B would be the dimension of k times the dimension of t, right? So k is Newton per meter. Okay. In other words, kilograms per meter squared, per second squared. That's k. Okay. You multiply this by the dimension of t, that's second. That will give you the SI unit of B. So what's the SI unit of B? That would be kilograms per second. So kilogram per second. And you divide by m, okay? You divide it by m. M is mass, so kilogram is gone. So what is B? What's the unit of B over m? That would be 1 over second. You see, it nicely cancels with t, which is in seconds. Okay, indeed, this is a dimensionless number, so the units work out really well. And secondly, take a look at this damping, that decay constant here. This is telling us that the greater the p-value, the faster it decays, right? The large p-value makes a quick decay. And that makes perfect sense because, after all, the reason why you have a decay in amplitude is because of the presence of this damping constant b, right? Without a damping force, if b is equal to 0, there is no damping, so of course, you don't have this exponential factor. So obviously, the damping gets faster when you have a greater value of b. It also makes sense that you have an m in the denominator here. What does that tell me? It tells me that for the same damping constant, for the same damping force, that is, if the object is massive, then the decay is going to be slower. That makes sense because if you try to slow down a very massive object from oscillation, it's not going to be very effective, right? If the object is not very massive, then you use the same amount of force of resistance. You can slow it down very quickly. So therefore, the more massive the object is, the slower the decay. So that also makes sense. This is how we express the rate at which the decay occurs. So we've learned that in the real world, there's always a decay going on, so that if you want to maintain the oscillation, if you want to make the oscillation going and going and going, you must somehow feed energy into it to replace the energy that's lost through the decay. Okay, this is the restoring force, and this is the decay force. Okay, this is the force due to the presence of friction. In order to sustain the oscillation, you must feed energy into it, so you must introduce a new term to drive the oscillation. So we're looking at what's called a driven or forced oscillation. There are different forces that you can use to drive it. If we're looking for a simple harmonic expression for the final oscillation, then it's clear that the force that we want here wouldn't be something really funny like a square wave or whatever. We want it to be just a simple harmonic variation as well. Okay, let's see, the amplitude of this force is F naught. Okay, and it also varies as a sine or cosine function of time. So let's say it's F naught times a sine function of time. Okay, sine omega t. Now, this omega, by the way, can be anything I want. This is how the force varies over time, and it is not necessarily equal to the omega of the free oscillation. If you leave this thing alone, it's going to have a square root of k over m, right? That is not necessarily equal to this omega. This omega is determined by the driver, okay, by the driver. So I grab this spring and I shake it, okay? Depends on how fast I shake it. It has nothing to do with how, the spring is going to oscillate by itself. So that's the force. And that equals mass times acceleration. Okay, mass times acceleration. So this time I have one more term here. The solution is a little bit more complicated. As a matter of fact, it consists of two terms, okay? There is a transient term, and that is, that term is going to go away over time. Okay, it only happens for a brief moment when you initiate the oscillation. And then it's followed by a steady term, which does not change over time, which goes on and on and on over time. Now, you can understand why there's a transient term. Imagine there's a spring and there's a mass, right? Nothing's going on at first. What you do is you grab that mass with its force, okay, and you start shaking it. Of course, the system is startled by that, right? It doesn't have an idea what's going on, right? It doesn't know how much force you want to pull it down with. It doesn't know how fast you want it to oscillate, right? So after a few cycles, okay, the system learns, oh, this is what you want me to do. You want to pull me down with this amplitude of force and with this angular frequency. So it learns to react, okay? There is a learning process which may take a few cycles. That is what's called a transient solution. We're not going to be bothered by that. Okay, we'll go straight into the next phase, and there is what's called the steady state solution. Okay, steady state solution. In a steady state solution, the amplitude of the oscillation no longer changes over time. Let's see physically why that is the case. Okay, because remember, the function of this term is to feed energy into the system. Now, initially, suppose it starts at rest. Okay, the oscillation starts at rest. So you take that force, you grab it and shake it, right? So initially, V is pretty small. You agree? V is pretty small. Okay, and of course, when you add this force, it's going to start oscillating, so V will increase. As V increases, this resistance force also increases. Now, this force feeds energy into the system. This force takes energy away from the system. Initially, because the motion is relatively slow, you feed more energy into it and less energy leaves the system. As a result, there is a net increase in the energy of the system, so the amplitude shoots up. Okay, it increases over time. Now, gradually, as the amplitude increases over time, V on average gets greater, so the resistance force also increases, and then the energy taken away by this resistance force also increases. Okay, so you have two competing sources. This one feeds energy into the system. This one takes energy away from the system. At some point, the average speed reaches such a value that the energy you feed into the system per cycle equals to the energy that's taken away by resistance per cycle. So what does that tell me? It tells me that at that point, when that stage is reached, there is no longer any net change in the energy of the system, right? Which means the amplitude of the system must be a constant. That is the so-called steady state solution. So in a steady state solution, I have just, a fixed amplitude oscillation. T and X. But please do not confuse this with a simple harmonic motion. This is not a simple harmonic motion. This is the forced harmonic oscillation. First of all, the frequency is not equal to square root of k over m necessarily. Rather, it's equal to whatever the driver wants. Okay, you grab it and shake it that fast, it's going to oscillate that fast. And if you grab it and shake it slowly, it has to do it slowly. Okay, the system has no choice as to what omega value it must oscillate with. That is dependent on the driving force. Okay, but that doesn't mean the system likes to be driven like that. The system can have its own reaction, right? It has its own reaction. Imagine, a child on a swing. Okay, you push a child on a swing like this, right? You know how you do that, right? When a child moves towards you like this, right? You don't push him back. Rather, you wait for him to come over and you give it a push, right? And the child goes forward with a greater amplitude. Then he comes back, you push it again, and it goes even higher. Comes back, push it even higher. Now, if the child swings like this, okay, by himself, like this, right? Like this. You don't want to grab his seat and shake it like this because, doing so is not going to be very effective in terms of increasing the amplitude of the swing. So that tells you that the system truly has no choice as to what frequency you want it to oscillate, but it does have a choice of whether it likes the frequency or not. By liking the frequency, what I mean is that you are using a frequency, driving frequency, which is close to the natural frequency of the oscillation. The system oscillates like that naturally, and you are pushing it also like that. So that pretty much at every moment, you are pushing it in the right direction. When the system moves this way, you're pushing it this way. When the system goes back, you're pushing it back. So essentially, you're always doing positive work to the system. Okay, you're not resisting the motion. You don't go out of sync with the system, so that when the system goes this way, you try to push it that, then you're doing negative work, right? Okay, so when you are applying a driving force with essentially the same frequency as the square root of k over m, by the way, that's called the natural frequency. Natural frequency. Omega, let's call it omega naught, just to tell it apart, k over m. Okay, here's the natural frequency. If the driving frequency is close to the natural frequency, then what happens is that the system moves in sync with the driving force. So the driving force always pushes the system in the correct direction, giving it positive work. And that dramatically increases the amplitude of the oscillation, so that if we say this is a situation where the driving force is either too fast or too slow, it doesn't give you a very large amplitude, right? And then when the driving force is just right in frequency, it can give it a very large amplitude like this, you see? Like this. Okay, so what you have here is a simple harmonic variation as a function of time. So it's like sine omega t plus phi. But there is an amplitude. This amplitude does not change over time because, remember, this force and that force, they do the same amount of work over one cycle, positive and negative, so the amplitude does not change. But it does depend on the driving frequency. Okay, if this driving frequency is close to the natural frequency, A will be large. Okay, because you're doing positive work, remember? And if omega is too fast or too slow compared with omega naught, the oscillation will not have a very large amplitude. So this is the physics. This is the representation of the so-called steady state solution. Now you can find what that A is. All you have to do is plug this into this expression, right? Into this equation. Of course, you have to take two derivatives here. You have to take one derivative here, and so on. You can match it. We're not going to be bothered with that. That's just mathematics, but it's a little tedious, but it's certainly doable. What we want to know is the physics, and that is, what is the shape of A omega? Okay, we know that if we plot A as a function of omega, there is one frequency that stands out, and that is so-called natural frequency of the system. Okay, natural frequency of the system. If omega is close to omega naught, the oscillation will have a very large amplitude. When omega is too large or too small, the response of the system will be weak. In other words, you get a smaller amplitude. So you can expect something like this. Okay. So you see, around that natural frequency, if the driving frequency matches natural frequency, you have the greatest amplitude. And when the frequency is too large, too small, you can have small amplitude. This phenomenon is called resonance. And this is called the resonance peak. Okay, you can draw two possibilities. Let's say you have a curve like this. In other words, there is a resonance curve, but it's not pronounced at all. It's very shallow, okay? Then you look at a different situation, like that. Look at that. That has the same resonance frequency as the first one, but the peak is very pronounced. Why is there a difference? Well, that depends on the mathematical details of A omega, which we're not going to get into. But physically, we can understand why there's a difference. If you look at these three forces, okay, now this force simply is responsible for providing the natural frequency. It's K, right? This force is the driving force. Okay, its frequency will determine whether the system will have a large oscillation, small oscillation. But what about that force? See, that is the resistance force. The resistance force is always opposite to the direction of motion, always slows things down. Does it care about whether the frequency is too high or too low? No, it doesn't. Okay, that term cares about whether the frequency is too high or too low compared with natural frequency. So the resistance force is insensitive to frequency. Okay, when B is small, then of course we're not going to worry about it too much, so that you have a very pronounced resonance peak like this. Because after all, this force, this term has an omega in it. When omega matches omega naught, you have very large oscillation and so forth. But when B is very large, then the system is dominated by the resistance force. You don't really care that much about, the next term, which is the driving force, so that the curve will not be very sensitive to frequency. So you get a flat curve like that. Okay, it is clear that in many situations we want a very sharp response like that. Now, in this situation, we say the system is highly selective. Okay, it favors this frequency very pronouncedly and rejects almost all other frequencies. Can you think of an application of a situation like that? Well, this is a very discriminating curve. Okay, it favors only this frequency, rejects everything else. Can you think of a situation where we want the system to be highly selective? Well, why not? How about a radio tuner, okay, or a television tuner? Our air is filled with all kinds of radio waves at all kinds of frequencies, right? How do you tune your radio so that you select only this particular frequency, okay, and reject all other frequencies? Because you don't want to listen to 2 radio stations at the same time, do you? Okay. And how do you do that? Simple. What you do is you tune the radio so that you adjust the natural frequency of the receiving circuitry. Of course, it's an electromagnetic oscillation, but the idea is the same. You are actually adjusting omega naught. Now, if omega naught matches the frequency of one particular radio station, then the signal from that radio station will enlist a very large response in your receiver, and neighboring stations with slightly different frequencies will be rejected. You see, so when you buy a radio or buy a TV set, you want a tuner that is highly selective so that you can pick up whatever frequency or whatever channel you want to listen to or watch. Okay, you don't want to buy something like that as a tuner, because then you're going to listen to a whole bunch of stations at the same time, because you see the response is not that different from one another. Okay, so that is the so-called resonance, and resonances have widespread applications in all areas of physics. It is sometimes a good thing, sometimes a bad thing. Like in the case of radio tuner, resonance is good. We want the resonance to be very pronounced. But resonance can also cause disasters. Okay, for example, if you have a bridge, the bridge, being a mechanical structure, has its own resonance frequencies. It may not have a single frequency because the structure is complicated. You can have several natural frequencies. What does that mean? It means that if a natural force grabs that bridge and shakes it with that particular frequency, which is close to the natural frequency, that's going to cause the bridge to shake violently because there's a resonance, right? So when you design a bridge, you want to find a way to calculate, to predict these natural frequencies. And you want these natural frequencies to be far away from the natural oscillation that can occur around the bridge. For example, wind. Okay, wind can blow on and off. It's like rocking, like a force rocking the bridge, right? But if the frequency due to the blowing of the wind gets close to one of the natural frequencies of the bridge itself, that can cause a very large oscillation in the bridge that can even collapse the bridge. And I'm not just saying that as a theoretical possibility. I mean, this has actually happened. In the textbook, you see a famous example, okay, of the 1940 turbulent winds that set up a torsional vibration in the Tacoma Narrows Bridge in Washington. This is page 474, and that caused the bridge to collapse. So when they designed that bridge, one of the natural frequencies happened to be around the frequency at which the wind rocks the bridge. So that was a structurally bad design. So you want to make sure when you design a bridge, you don't design a bridge to have a frequency that is close to this range, so you can